Hi class. So one of the more common ways that we can improve the results of our shading is a technique called texture mapping, and this is pervasive in computer graphics. And here's the basic idea. When we're shading, right, we're on the raster, we're filling in that triangle. Instead of calculating it with a lighting system or from a basic flat color, we actually select the color from a texture. We select the color from an image. And this is a raster image. Okay, so we select the color from a raster image source. Now this term here, raster image, this is called a texture. So it's just an image, but when it's used to cover a surface with shading, we call it a texture. Okay. Now the primary reason why this idea took off is that it's effective and fast, because we can greatly increase the detail. So we can greatly increase detail without increasing geometry. Increase. I mean, you might think this is useful for things like pictures. Yeah, we can put a picture of a sky up instead of rendering it with geometry. But a lot of times you look at your model and go, maybe I can replace that with a picture that looks like the geometry I want. And now I just have to fill in a couple of triangles instead of drawing a very intricate shape, okay? Now this image itself, they can be loaded from a file. Which is probably the more common thing that we do, or we can actually procedurally generate them. So you can generate your own textures based on some code you're running. And the reason why you would do that instead of just putting it into geometry is if you procedurally generate something as a texture, this supports reuse. So imagine you had something you wanted to generate and use in 4 or 5, 6 places around the scene, or you wanted to generate it once and put it back up like a mirror. You might want to generate the scene from this direction and then draw it on several mirrors. You can reuse that work. Okay, so we can do that. I'm going to jump over to the slides and we'll take a look at what this looks like. Where are we? There we go. So here, this is texture mapping. Here's a basic idea. Instead of drawing an object like this, like a cube, and you put flat colors into sides and some basic lighting going on here, which is why you have the shading, you put a picture on here. And as you can see in this example, the picture actually looks quite nice, and there's a lot of detail here. The raised piece here that you might think, oh, let's do that in geometry with you know, triangles, but we don't have to. We can get away with doing it as a picture. Oops, here we go. In the early days, this was a huge shift. So this is one of the very first 3D computer games, MIDI Maze from 1987, a very long time ago, and it was all flat shaded, as you can see. When they added textures, now look at all the detail that you can see on the walls, and it looks much more 3D than this flat shaded. The floor is still flat shaded, and we have bitmap enemies and bitmap hands and all these things. But this texture mapping on the wall here was a huge boon for the quality of the graphics. Here's an example from Wikipedia. This is a tank with some random flat shading thrown on just to show you the different surfaces. And then there's some really intricate geometry like the guns and the wheels, but then when we put textures on, we can do decals, which are quite nice, you know, these decals here. But you can also do things like the tracks. The tracks you would typically think of doing in geometry, but with texture mapping, we don't have to. The ridges in the side of the tank we can do. So you can fill in a lot of these little details, the headlights and whatnot. Look at that. You can fill in those little details with a picture and not with geometry, which saves you a lot of work. So that's texture mapping. Now the one thing I will mention, I should probably write this in the slides, slide 13 to 15. The one thing I'll mention is that we typically do texture mapping during, what's going on? Huh. We typically do texture mapping during rasterization, okay? So we do it at that last phase when we're drawing the triangles on the screen. Generally happens during rasterization. And the reason we do that is because it's so expensive. It's actually not fast. And if we texture map things in the scene first and then put them and then transform them onto the screen, then you waste a lot of work, and because it's expensive, we don't need to do that. So you typically do it at the last mile. When you have your triangle on the screen, you're shading that triangle, that's when you do your texture mapping. So texture mapping is fun, it's great, but there's a basic problem that we have to overcome to make this work. So the basic problem of texture mapping: which image source pixel, which pixel from the source image do we use? Oh, I should go back to my slides. There we go. So the basic problem is, which source pixel do we use? We're drawing our triangle, we're shading a triangle, we have to choose which one to use. So which source image pixel to use? Now I'll give another keyword here. The source image pixel, if you're getting a pixel from a texture, we have a special word for that. This is called a texture pixel, right? Because it's a pixel in the texture, but we actually shorten that to be a texel. So a texel is just a pixel that's coming from the texture, and we use this to differentiate during rasterization. If I say pixel, we're talking about the raster. If I say texel, we're talking about the texture that it's coming from. Okay. All right. Okay, I actually paused the video here. I brought in this picture. I didn't want to waste time. This is an example that I might be using for a texture image. And what I'm doing is, this is in, my texture space. I have it in my little coordinate system, whatever. And I have this triangle I'm filling in. I'm shading this. This is happening during rasterization. Okay, so this is my basic problem. I have a point. I'm here. I'm at point P. Which point of my texture do I use to fill that in? So that's the basic problem of texture mapping that we need to overcome. So the first thing we do is we specify some region in the texture that corresponds to our geometry. Okay, so I can go, all right, I'm going to shade this triangle just like that. Cool. That's the first thing we do. And once we specify that, then we map the image somehow. Map the image from the texture, from the defined region, onto the final raster region. So just like that. We take this texture image and we start filling in our dots here. So that's what we need to do. I'll mention a few things. More generally, we need to set this up in a very robust fashion, okay? Because it needs to work even when our geometry gets transformed. So it needs to work robustly and stay consistent. Even when the triangle rotates or gets transformed or scales, okay? So even as the triangle gets transformed. Right? So the basic approach that we do is we define, here we're talking about rasterization and texture image. We actually take a middle ground. We define the texture coordinates, or the texture mapping, we define the texture mapping in the object space as an intermediary. So when you're defining your object, you define the texture space there concretely. And then we got to find some way to convert that onto screen to raster space. And we'll talk about that a little later. But first, I want to mention there are actually two approaches to this. There's what's called forward texture mapping. Now, forward texture mapping is where you set up this region like I just showed you, and then you take your texture and you work from left to right. You go this way. I'll write forward here. So you take this texture and you map it onto the triangle and you squeeze it in or squish it as it needs to or rotate it as it needs to, but you solve it in that direction. So you go through every texel and find out where it goes onto the raster. So we transform the texture onto the triangle. Okay, and then you draw that on the raster. So this actually works fairly well. Some early video game systems, I believe the Sega Saturn, used to do this because you can actually save a lot of work in terms of fixing problems that come up, as we'll learn later in this unit. A lot of the problems that come up because of the other method we're going to use don't happen here, so you can save a lot of work. However, the downside is you're likely to double up your work. You're likely to have multiple texels. Per pixel. And I won't even talk about the other direction where if your texture is too small and you have to stretch it out. But even if it's too big and you stretch it down, you're going to have spots where multiple texels go into the same pixel. Now we have, do we do anti-aliasing? Do we do subpixel rendering? Do we just replace it? We have to make some choices. So that's the biggest problem with forward texel mapping, forward texture mapping, is it can be very wasteful. But the upside is, yeah, a lot of the problems that we use, we come across with aliasing and things in the other direction, they don't happen as much here. So the other approach is called inverse texture mapping. Now, inverse texture mapping, as you might have guessed, this is inverse. This goes the other way. And the way that inverse texture mapping works is as we're scanning, okay, we calculate the texel during that process. So we calculate the texel during rasterization using the pixel coordinates. Okay. This is nice because we guarantee each pixel only gets drawn once. And you should have learned that in your earlier, you should have learned why when you learned about scanline filling. So we guarantee each pixel is only filled once. So we save a lot of work. Okay. The downside is with this approach you can actually get a lot of artifacts which don't look pleasant. But we'll come back to that. Okay, we're not going to handle that now. All right, so that's the basic problem and introduction to texture mapping. So we'll spend the next few videos talking about how to make it work and some of the problems we'll come across.